So let's talk about the basic components of electricity, whether you know it or not. When you're charging up your computer, you're working with voltages and currents. So let's talk about basic electronics. Power is work over time. It's measured in watts. Your light bulb, 100-watt light bulb, you go home, turn on your lamp, 100-watt light bulb is doing work power by emitting light, and it's taking voltage and current and making power out of it that you can see in terms of light. An amplifier has a certain power, and that has to do with how much it can move the speakers and what size speakers it can move and how much work it can do over time to move the cone, which generates an air disturbance, which generates the power in the sound wave. So power is work over time. Voltage is a potential energy in a circuit. Current is interrelated to voltage, and current is the rate of flow of electrons in a wire. Let's think of one wire, okay? You've got a wire, just for the time being, think of it as a garden hose. You've got water on one side pushing through the hose. Turn on the spigot. The pressure that the water is going through the hose with would be similar to what voltage is. How much water actually goes through the hose over time is the rate of flow of the electrons, and that's similar to current. Impedance is another term that we use all the time, and it's the opposition to the current flow. There's also another term, which I didn't include on the card, which we'll talk about quite a bit, called resistance. It resists the current flow. You might say, what's the difference between impedance and resistance? Impedance is the opposition to the current flow and is frequency related. So you have high frequency or low frequency. It changes how much it impedes the flow of the electrons. Resistance, it's non-frequency related. Power in a circuit is the measure in watts represented by P. There's a couple other ways to represent power, like horsepower, right? You think of your car as horsepower. That can actually be converted into watts, because watts and horsepower are both measures of power. Voltage is potential energy of an electric circuit measured in volts, represented by V. Current is the flow of energy within a circuit measured in amperes, represented by I. Amperes or amp. Resistance. Resistance to the electrical flow of electrons. Something with a measured resistance is called a load on the circuit, and it's measured in ohms and represented by R. Now, it kind of makes sense to me a little bit when you think about what electrons do in a wire. They have to flow from atom to atom to atom and move along in the wire, and it needs some sort of energy to push it along. And that would be voltage, pushing the electrons to flow through a wire. And the resistance of the electrons to flow through the wire would be called the resistance. You have a resistance in a wire and you have electrons flowing, you'll eventually generate some heat, friction of the electrons moving through a wire. Now that's any wire. We always represent wires and cables in the studio as being perfect and no resistance at all, but they all represent some small, minute resistance to the signal flow from one piece of gear to the next. And that's where you get into the monster cables versus not monster cables. And they charge you 3-4 times as much as a regular cable because they've made a cable specialized in trying to minimize the resistance of electron flow by the way that they've internally constructed the cable. Is it worth it getting a monster cable? That's sort of a personal judgment. Technically speaking, they have a point of what they're doing is correct, but I doubt you can really hear it. Gold is a better conductor than silver, so if it's more conductive, it has less resistance. Impedance is the resistance to flow of energy in a circuit, very similar to resistance, except it has to do with different frequencies being treated a little differently. There are components that are frequency dependent, and that matters to us because once we transduce a sound from the acoustic domain through a microphone into an electronic signal, it has a spectrum, and that spectrum goes up infinitely. And so the higher frequencies being treated differently, just moving through a cable or through a piece of electronic gear, will actually affect how it sounds at the other end of the chain. So there's a basic law of electronics, very simple interrelationship between these three component values that we use as our basis for electronics: voltage, current, and resistance. Which kind of makes sense because if you have less resistance in a wire when you're trying to push the same amount of pressure on the electrons, or let's say your water hose, same amount of pressure, except there's less resistance to the water flow, you're going to get more water flowing. If there's more resistance to the water flow because the hose narrows in one area, then you're going to get less water flow with the same amount of pressure. The basic law, it's called Ohm's law, is voltage equals current times resistance. If I wanted to find the voltage, I would multiply the current times resistance. If I wanted to find the resistance, I would take the voltage and divide it by the current. If I want to find the current, I take voltage divided by resistance. Okay, the next law that's important is called Power's law, or Watt's law. Power equals voltage times current. And you can make these two formulas interact because we know that voltage is current times resistance. So not that you need to know any math, it's just interesting how these three components sort of react and interact with each other. Audio is considered low voltage system if the voltage is below 70 volts. For example, a lot of the PA systems where somebody can actually announce from a central location, those are low voltage systems. Or in a shopping mall that plays music, those are low voltage systems. They're safe most of the time. Somebody can hook it up without having a license to do so. High voltage systems, on the other hand, are 70 volts and greater and can be dangerous. So you need a license to be able to install them, and they can potentially actually really hurt you. Because voltage, when it gets up to a certain amount of voltage, means there's a lot of pressure pushing electrons through whatever it can push it through, whether it's a wire or whether it's through a human body. I don't know how many people have had those 9-volt batteries. The guitar players, I'm sure, have all had those 9-volt batteries in their foot pedals, right? And to test it, to make sure it's working, you touch it to your tongue. And if you feel a tingle, yeah, that's good. It doesn't hurt you because 9 volts is pretty low voltage, and the battery doesn't have a lot of electrons to push through, so the current is pretty low. So it really can't hurt you, but it can give you a little tingle. How many people have accidentally taken a knife and stuck it in a toaster to get a piece of toast out? Anybody? Okay, I'm the only stupid one then. So it can be pretty dangerous. The higher the voltage, the more danger there is, because the higher the voltage means how much more pressure there is if you connect with it to push electrons through whatever it can push it through. And it doesn't have to be a wire. It can be my body, it can be my finger, it can be my arms through my chest, where my heart is, and really mess things up. So you got to be careful. And part of this week that we're talking about electricity, we'll talk about how gear manufacturers, computer manufacturers, phone manufacturers actually design for safety because they don't want anybody to be shocked or even get any stray electricity. Direct current, alternating current, AC and DC. Direct current is a positive potential that's a steady potential that doesn't deviate from its voltage. So what would be something that uses DC power? A battery, your iPhone, a flashlight, they use DC. AC is an alternating current that fluctuates around a center point. Let me give you a few little pictures. That's DC, so there's a steady voltage and a steady current. AC is an alternating current. So where is AC found? AC is found out of the plug in the wall. That's 110 volts AC. In other countries, it's 240 volts, 220 volts. In Japan, I think it's 100 volts. We adopted 110 volts as being our standard here. And it alternates 60 times a second. Is there a reason? Yes, actually there is. Okay, let's think about it for a second. If we talk about voltage and current, and a direct voltage being a direct pressure on the electrons to move through a wire, and let's say we had 100 volts direct of direct current, it would be much more dangerous than if we had alternating current. So as we discussed before, every wire acts as a resistance to the current flow. So if we had a direct flow, you'd generate a certain amount of heat distributing power, say, from the Hoover Dam to Los Angeles, going through all of those wires. Now, if it's AC, it's going to be fluctuating positive, negative, positive, negative. That means that it's going to be a lot less friction. So therefore, you can use thinner wires. It's also safer in case we happen to touch it because it's not just direct pressure of electrons flowing through your body, it would be alternating. The other thing is, as I mentioned before, each country has adopted their own standard voltages out of the wall. And I always thought it was a little odd because you go to Europe, you got to get an adapter, it's like different than American standards and all that. And I just chalked it up to the fact that in England they drive on the other side of the road, everybody's got their own thing. But actually there's a real reason why in Europe they use 220 or 240 volts and we use 110. at 60 cycles per second. They use 220 at 50 cycles per second. Now, the reason is that when you think about all of the power distribution of going in a city from the main power plant to all the little substations to the houses and so on and so forth, and we talked about what power is, because essentially at the end of the day we want to turn on a light bulb, which is 100 watts, use some power. So if we have 100 volts coming out of the wall and we've got 100 watts of work we want to do, that would mean we need 1 amp of current flow, right? 1 times 100 volts would be 100 watts. Now in Europe, if we wanted to do 100 watts of work and we had 200 volts coming out of the wall, we would only need a half of an amp of current flow. So less current flow, meaning less electrons flowing through the wire, means that the wires don't get as hot, there's less friction, and therefore they can use thinner wires. And if that happens, then it's much cheaper and easier to do power distribution than it is to use thicker, heavier, more conductive wires. But it dawned on me that there's a real reason why everybody chooses a different standard. Now there's one key issue that we didn't discuss in terms of electronics that I think is very critical. For example, we discussed what potential is, but it has to be potential related to what? Related to a baseline of no volts. So if we're talking about volts being a potential difference in the amount of electrons that it would make move, we have to have a reference of what 0 volts is. That's where we get to ground. It's called ground because it's 0 potential. It's our reference potential, and it's usually tied to Earth, believe it or not. Ground is ground, and all of these terms started, I think, when Benjamin Franklin was, lightning and all that, the potential out of lightning and Earth. And the reason lightning actually hits Earth is because it's going towards a 0 potential when there's a potential in the clouds in a storm of a voltage, a static potential, and then you get a lightning crack and it hits Earth because Earth is 0 volts. All electrons always strive to go down to 0 volts, 0 potential. So ground is another term that's really, really important, and we'll discuss it as to how it's involved in making your sound system quiet, making your speakers not buzz. Why is there a buzz in my microphone? We can get rid of all that if we understand what ground is and what stray potential is.